Polynomial interpolation involves fitting a polynomial through a set of points. So we have the coordinates x1, y1, x2, y2, and so on up to xn, yn. So given this set of points, where the x coordinates are distinct, then there's a unique polynomial which has a degree that's less than or equal to n minus 1 that passes through these points. So we can write this polynomial using the coefficients. So a0 plus a1x plus a2x squared, and so on, up to the coefficient an minus 1 by x to the n minus 1. So given this interpolating polynomial has to pass through these points, then the coordinates must satisfy the following equations. So if we just copy this equation out, so our first equation involves the coordinates x1 and y1. So we'll just replace these variables with x1, and that's equal to y1. And similarly, the second equation that must be satisfied involves the coordinates x2, y2. And this continues on and on up to the nth coordinates. So we have a system of linear equations to solve for these coefficients. So let's write this in matrix form. So for the first equation, corresponding to the coefficient a0, we have 1, and corresponding to coefficient a1, we have x1, and a2, x1 squared, and so on up to x1 to the n minus 1. So you can visualize this a bit better if we just multiply this by the vector of coefficients. So we have a0, a1, a2, and so on down to an minus 1. So in the next row, we have 1 by a0, then x2, x2 squared, and so on up to x2 to the n minus 1. And this continues on and on down to an minus 1. So we have 1 xn squared up to xn to the n minus 1, as we can see. So we had n equations. And the first equation is equal to y1, the second one y2, and similarly you'd have y3, and so on down to yn. And we're going to use this method to solve integrals numerically by solving this system of equations for the polynomial coefficients to get a polynomial that passes through the given set of points. We can approximate integrals using simple numerical methods such as Riemann sums, the Simpson rule, Gauss quadrature, and so on. But let's approximate this integral using polynomial interpolation. So this is a well-known integral that cannot be evaluated analytically because we cannot express an antiderivative of this integrand in terms of elementary functions. And now let's break up our interval, where we're evaluating this integral, being from 0 to 1, into increments of 0.25. So we're going to choose our first x-coordinate at 0, our second x-coordinate at 0.25, our third one at 0.5, and then x3 is at 0.75, and finally x4 is equal to 1. And now using the integrand, we'll compute f of x0, which is e to the 0 being 1, and then f of x1 is e to the 0.25 squared, and f of x2 is e to the 0.5 squared, and so on. So we have f of x3 is e to the 0.75 squared, and f of x4 is e to the 1 squared, which is e. So in this case, the number of points are 5. So the polynomial that we're looking for has a degree equal to 5 minus 1. So it's equal to a0 plus a1x plus a2x squared plus a3x cubed plus a4 x to the 4. And now we'll construct our matrix, being an augmented matrix, to solve for these coefficients. And we have the y values in the far column. So we have 1 e to the 0.25 squared, e to the 0.5 squared, e to the 0.75 squared, and e to the 1. And then in our first equation, we have a0 by 1, and a1 by x0, where x0 is 0, a2 by x0 squared, so 0 squared is 0, a3 by 0 cubed, and a4 by 0 to the 4. And we use x1 in our second equation. So we have a0 by 1, a1 by x, which is 0.25, a2 by x squared, so we have 0.25 squared, a3 by x cubed, and a4 by x to the 4. And for our next equation, we use x2. So we have a0 by 1, a1 by 0.5, a2 by 0.5 squared, a3 by 0.5 cubed, and a4 by 0.5 to the 4. And then we have x3 is 0.75. So in our next equation we have 1, 0.75, 0.75 squared, 0.75 cubed, and 0.75 to the 4. And finally we use x4 is equal to 1. So we have a0 by 1, and then a1 by 1, a2 by 1 squared, and 1 squared is 1, 1 cubed is 1, and 1 to the 4 is 1. And now we can solve this system to obtain the coefficients. So typically, you'd reduce this to reduced row echelon form. And then you'll get the coefficients in the right column, which I'll let you do as an exercise. So you'd get the following results. So now we have a polynomial with the known coefficients, which you can substitute into this integral to replace the integrand, and you can evaluate the integral by the power rule. Let me make some space here. So the approximation to the integral that you'll get is 1.463. And now if we look at our plot, we can see that our polynomial, which is the red curve, approximates e to the x squared quite well over the interval from 0 to 1. So we can see the area under the curve given by the integral is around 1.5. Now if we approximate the area under the curve using two trapeziums, so we have one trapezium up to 0.5 and another trapezium up to 1. So the area of the first trapezium is e to the 0 squared, which is 1, plus e to the 0.5 squared, onto, multiplied by the length, which is 0.5, and plus the area of the second trapezium. So I have e to the 0.5 squared, plus e to the 1 squared, onto, times the length of that trapezium. So this gives a slightly larger area than the approximation we obtained using the interpolating polynomial. So here we get 1.572. And as you can imagine, if these trapeziums were smaller, so you break this one in half for example, you'd get an even better approximation to the area under the curve.